And as far as today goes, yeah, we're going to knock out Chapter 10, and it depends on how much time we have left over. We might just do the review session here. We might need to head to the chem lab, but I'm thinking it's going to be in here. Okay, so this is my first semester. This is my first semester actually to include the chapter on extrasolar planets, because, I mean, who hasn't thought about, like, life out there, for one, and they got to live on a planet, right? The other thing is, when we talk about the chapter about the sun, we're actually going to see that the sun is going to, it's not going to blow up, it's not going to go nova or supernova or anything, but it's going to expand, and it's going to, I think, go out to the, like, Mars or something. I mean, it's basically, Earth's going to be crisped in about 5 billion years. So we need to be thinking about these things. Okay, so extrasolar planets. This is a good slide because this slide actually says that this actually is a direct look at a star. There's a star in here, and a lot of times, one of the things it's hard to find planets that orbit other stars because the star's so bright. So what they have to do is basically block out that light, and this is a rare situation where we actually see the planets visually. It's direct detection, which doesn't happen very often. Okay. So the term extrasolar planets means basically a planet that orbits another star. Okay, extrasolar planets. And it amazes me. Actually, we find that most stars up there have a system of planets orbiting them. Most stars that we've looked at. But as of 1992, we thought, no, not much. Okay. There's this thing called the Drake equation, which you may have run into if you watch The Big Bang. Sheldon is, I'm sure, a firm believer of the Drake equation, right? The Drake equation says, is there life out there, intelligent life out there? And one of the factors is, are there planets that intelligent life could evolve on? So anyway, it just amazes me. So we talked about the formation of our own star system, our own solar system and planets, and we call that the nebular theory. So honestly, I don't think it's much of a stretch to think that other stars, as they formed, also had other planets forming in orbit about them too. So since 1992, we've just been kind of cranking out the whole extrasolar planets thing. But remember that slide we saw, that kind of opener, most extrasolar planets, you don't really actually get to get a little picture of them. Okay, they're mostly known indirectly. So this I kind of mentioned right off the bat. Why is it hard? Why is it so challenging to find these extrasolar planets? Because the star is so dang bright, and the planets are so darn small compared to them, and the whole system is so far away. So you're like, it's challenging, but something tells me that the scientists like this like a challenge. So how do we see them or detect them? If we don't detect them directly, we detect them indirectly. And there's two ways to detect them indirectly. Okay, and there's like a figure that goes with both of them. So one way is that actually the extrasolar planet we're looking for is big enough that basically it affects the star. So the star will kind of wobble depending upon the planet as the planet orbits the star, okay? And we get to see that wobble. Now, actually, there are two ways we can see the wobble, too. But up there in the upper right-hand corner, it says the sun. And this sort of wobbling, actually, our sun does it a little bit because of Jupiter. Jupiter's like humongous, right? And so our star does kind of wobble. If somebody was looking at our star to see if it had planets, they could see. If they could see the wobble of the sun. So the two ways that we can see this wobble, astrometric, I was like, I don't know, it just sounds like a scary word. But astrometric just means that you see the star move against the background stars. That's it. Astrometric just means that you're looking at a star map and you see a wiggle. Okay, that's it. Doppler, we've talked about the Doppler effect before. The thing about the Doppler effect is it has to be along line of sight. It has to be what we call radial motion, not proper motion. So astrometric if it's proper motion, I guess, and Doppler method if it's radial. So that's one way, to look at the wiggle. The other one is to look at the light curve. So here's the deal. Over here on the far right-hand lower, we have some light curves. And basically, and this has to be kind of oriented right too, it has to be oriented right just like this. So if my fist is the star and my finger is the planet, okay? Basically, when you have the planet and the star, you have all the light that's possible. Okay? As the planet goes in front of the star, it's not much, but as the planet goes in front of the star, it, what we say, eclipses a little bit of the star, so your light meter goes down. Okay? As it goes over there, your light meter goes back up again. Okay? As the planet scoots around behind the star, actually the light goes down a little bit too. Okay, so you have down, and then otherwise it's up. So you look for that pattern, and I just, and do you see where it has to be kind of line of sight too? If it was like this, okay, you would not see any eclipsing, okay? So again, it's a orientation sort of thing. There are actually, there was a Kepler spacecraft that actually, that's all it did. It, well, I think it's still up there, but I think it ran out of juice. Kepler spacecraft. And so a lot of these actually, you'll see Kepler, the Kepler planet system. And it's just because that was the spacecraft that took the pictures that they ultimately were able to find the extrasolar planet. So. All right, so what can we know about these planets, these extrasolar planets? Well, quite a bit. Okay. We can get, the period is how long they take to orbit their star, the distance from the star, kind of the shape of the orbit, that's the eccentricity. We can ultimately use Newton's laws, isn't that awesome? To, again, it's the period and kind of get the mass of the star, and to get the mass of the planet. Is that not awesome or what? Another thing is we can, depending upon how we detected it indirectly, get the radius of the planet. And from mass and radius, we can get density. We can, like if we're looking for a place to land, right, we can actually get information about the atmosphere around the planet, okay, using stellar spectra. So, I don't know, pretty cool. So here's Kepler 11 planetary system. Again, Kepler is just the spacecraft that I think they're still crunching the data. This would be from the eclipsing method. So, of course, probably what we want to do is compare any of our extrasolar planets with planets that we have here in our own solar system. You know, if we're looking for a candidate to get in a spacecraft and drive to, right, we want to have a sense for that. But reality is that they are finding very few Earth-like planets. Every once in a while, it'll be in the news, be like, oh, they found a match for Earth, you know, analogous planet in another star system that's like Earth. More than likely, though, we're finding these large planets, and that makes sense because, you know, the bigger they are, the easier they are going to be to find, okay? So most planets are kind of these large planets, gaseous planets. So of the stars that they've surveyed and have been able to indirectly find extrasolar planets, 70% have been positive with regard to at least one planet. Okay. The densities of the planets, which we've kind of talked about density, of course the gaseous planets are really light and the terrestrial planets are very dense. Okay, they run the gambit from just a nugget of iron to styrofoam. Yeah. Last slide. This is a very busy slide, but basically, you know how we talk about our solar system, and you probably learned it before, you know, the whole Mercury, Venus, Earth, Mars, or the terrestrial planets, and then we have the gaseous planets. In our solar system, they're kind of finding that there's kind of some different sort of variations out there. All right. So